So just so that you know, this is a sort of an overview of principles of quantum networks. There are two of us that are going to be sort of lecturing. I'm Don Towsley. I'm a professor at the University of Massachusetts at Amherst. And my colleague, Matheus Andrade, who's a PhD student at UMass, will be the co-instructor. Okay. Before we go on, however, I'd like to do a poll to find out what the backgrounds are of all of you in terms of quantum information and then classical networks. If you could just sort of let us know what your knowledge is. I presume that some of you have been sitting in on the earlier courses as part of this winter school, and so hopefully you're starting to get some background in this.
So yeah, I think we had a problem with the wordings in the answers for the poll question. So A means high and E means no knowledge, pretty much.
Okay, yeah. So it looks like it's sort of pretty much split. I guess many of you have some knowledge, which will be good because although we're going to have a little bit of an overview, it's not going to be intensive. Let's go to the next poll question, which is one of the things that we're going to be doing in this short course is sort of relating quantum networks to classical networks. And so I'm curious, or we're curious, what kind of background you might have. Okay.
This poll is also just going to be A, B, C, D, E. I'm sorry about that, Don, Matheus.
Oh, sure.
No problem. Again, A is high and E is low. E is no knowledge.
Okay. So I think some of you will find the material where we try to relate classical to quantum sort of new to you in terms of classical networks. Some of you, it'll be sort of a review. And I hope that as we go on, you'll sort of see what the parallels and the contrasts are between classical and quantum networks. Next slide, please. So I just want to quickly tell you the outline, and then I'm going to hand it over to Matheus, who's going to start with the introduction. There's a sort of a short introduction to quantum networks, really sort of the quantum aspect of it. And then I'm going to speak for 45 minutes on classical networks and how they compare and contrast with quantum networks. I think then we'll take a short break. And when we come back, Matheus will talk about network management and quantum tomography, which relates to sort of doing end-to-end measurements and trying to understand the behavior. And then we'll switch back to me, and I will talk about sort of, what's the performance of these networks, how do you do resource allocation, how do you do scheduling, and then we'll finally summarize. And throughout, we'll have a number of poll questions just to see that you sort of caught what we've been trying to get across. I'll turn it over to you now, Matheus. Thanks.
Thank you, Don. Yeah, it's my absolute pleasure to be here with you all today. So let's start by having a brief overview of what the quantum internet means. Well, essentially, the vision of the quantum internet is to interconnect quantum processors and enable quantum connectivity between multiple user groups. Essentially, this has a strong parallel with the way that classical networks operate, since they enable multiple classical computers to intercommunicate, and there's plenty of different access to to networks formed by multiple users. And the idea is that the quantum internet will enable this network users to perform very interesting applications that cannot be implemented with classical communication alone. And the key ingredient for quantum networks is quantum entanglement, which is essentially the property of quantum mechanics that really distinguishes quantum systems of classical ones. And the fundamental entangled states that we're going to focus today is the Bell state, which is the quantum state of 2 qubits. And we can imagine that these 2 qubits are sitting in different processors, let's say Alice and Bob. And the Bell state is a state that reads as follows. It's 0, 0 plus 1, 1 over root 2, again, where each one of these qubits sits in a particular quantum processor. And there's a very important aspect of Bell states that distinguishes them from the states of classical bits. So let's use a brief analogy here to understand what we mean by this special property. We can correlate the zeros and ones with states of a coin, let's say heads for 0 and tails for 1. And in this special state, if Alice performs a measurement on its coin and it sees a heads, and if Bob then later on performs a measurement on his coin, he will also see a heads. And this was what Einstein called the spooky action at a distance, because the act of measuring one of these qubits in Alice gives you knowledge about the outcome of the measurement in Bob. And this is so fantastic that it yielded the Nobel Prize of last year, awarded to Aspect, Clauser, and Zeilinger for experiments that enable the validation of the experimental validation of these properties of entanglement, and essentially ruled out that classical theories could explain these sorts of behavior. And why are we talking about the quantum internet? Well, it's because of the applications that the quantum internet will enable. One of the main applications is quantum key distribution, which essentially works for cryptography and security, where processors distribute shared keys that with a security guarantee backed up by the very laws of quantum mechanics instead of laws of computational intractability. This, which is essentially the main principle that the current distribution protocol, the key distribution or security protocols work today. The quantum internet will also enable small quantum computers to be working together and solve hard problems in a similar fashion that how the classical internet enable classical computers to do distributed computing. We can think that it's much easier to build small quantum processors and interconnect them, and allowing them essentially to become a big virtual quantum machine to solve problems than build a big monolithic quantum computer. And finally, another leading application for the quantum internet is high resolution sensing, which essentially uses entanglement to enhance the efficiency of sensors, for instance, let's say, of telescopes spread across the globe to probe stars, for instance. Okay, so now let's dive a bit deeper into the Bell state. Again, the Bell state is a state of 2 qubits, 0, 0 plus 1, 1 over root 2. And the idea is that if one of these qubits sits in Alice and the other one sits in Bob, and if Alice performs a Z basis measurement on its qubits, the outcome of this measurement will be the same outcome that Bob will see if it measures its qubits in the Z basis as well. So to be clear here, if Alice performs Z basis measurements and see a 0, then Bob will also see a 0. If Alice sees a 1, Bob will also see a 1. And this is right out of the box very important for distributing shared randomness across large distances. You can imagine that as soon as Alice and Bob share a Bell pair, when Alice performs its measurement, the outcome of this measurement is a random variable, meaning it's a random bit. And Bob will see the exact bit that Alice sees once it performs the measurement. And this Bell state is a very fundamental ingredient for quantum teleportation, quantum key distribution, sensing, and distributed quantum computing, which are the fundamental applications that a quantum internet will provide. There's a very nice extension of Bell states to multiple qubits, which we're going to use once we talk about network management and tomography. And the state is called the Greenberger-Horn-Zeilinger, for short GHZ state, that describes multiple qubits. So instead of just having 2, now we have n qubits, and the state just reads n zeros plus n ones over root 2. And again, this is a very fundamental state for many different quantum protocols. And we can imagine now, if we look at a simple case of 3 qubits, we now have a very strong correlation between 3 coins, quantum coins, generalizing the notion of the Bell state, which is a very special state for 2 of these coins. Okay, so now let's talk about a bit of quantum teleportation, which is, again, a way that we can transmit quantum information using quantum networks. Let's imagine that Alice and Bob share a Bell pair, which we are calling here an end-to-end entanglement, depicted by these blue circles. And let's suppose that Alice wants to send a qubit to Bob, which we show here as this star qubit. Then, having this Bell state shared between Alice and Bob, Alice is going to perform a very particular type of operation with the qubit that he wants to send, and its end of the Bell pair. Once this operation is done, Alice will perform a measurement on these 2 qubits, which will yield 2 bits of classical information. Then Alice sends these 2 bits to Bob, and these 2 bits will be used by Bob to perform an operation that depends on these 2 bits in order to get back the star qubit that Alice wanted to send. And the circuit, the quantum operation that is performed by both Alice and Bob, is shown here in this circuit. Let's imagine that Alice wants to send the state psi equals alpha 0 plus beta 1 to Bob, and that both of them share this Bell pair, 0, 0 plus 1, 1 over root 2. Then Alice will perform a C0 controlled by the qubit that it wants to send to Bob, targeting its end of the Bell pair. Then it will apply a Hadamard gate on the qubit that it wants to send, followed by Z basis measurement on both of the qubits. Then these bits are sent to Bob, which is depicted here by these parallel lines. And based on the values of these bits, Bob will perform an X measurement if the bit B is 1, an X gate if the value of B is 1, and a Z gate if the value of A is 1. And once Bob is done with this 2 operations, this qubit that started as Bob's end of the Bell pair becomes a state psi. And it's very important to emphasize here that this process does not involve any transport of quantum information from Alice to Bob. We start the process with a Bell pair, and once we have that Bell pair established, there is no transmission of a qubit from Alice to Bob, just the classical bits that are obtained from the measurements that Alice performs. But why is our quantum communication so hard? Why are we talking about methods and the similarities and differences of quantum and classical networks? Well, there's a very intrinsic difficulty of performing quantum communications. Let's imagine that we have Alice and Bob and that they have a fiber connecting them. And the length of this fiber is L. The rate that we can distribute entanglement between Alice and Bob, that we can share Bell pairs between Alice and Bob, decays exponentially with the distance between these 2. So then a very naive question that comes right after this is, okay, we have all this strong attenuation. Can we use classical techniques like signal amplification to boost our ability to transmit entanglement between Alice and Bob? Unfortunately, the no cloning theorem tells us that we cannot perform this amplification. And this leads to a whole new notion of overcoming this exponential decrease with distance, or decay, this decay with distance. So let's run a quick poll question here to see how things are going so far. The question is, How does the generation rate of EPR pairs decay with distance in direct transmission through fiber? So A, polynomial decrease, B, constant decrease, C, exponential decrease, D, depends on the fiber technology used, or E, I don't know. Yeah, so we had a question here in a Q&A that is, does the value of rate correspond to the likelihood of success? Yes, you can imagine this way. The rate here means the likelihood that you'll see if you send a photon from A to B, that you'll see this photon reaching B, essentially. Okay, so we see the results here. We had some people saying B, a constant decrease, C, exponential decrease, and D depends on the fiber, with a large majority on C. And yes, this is the correct answer, exponential decrease. And to be fully precise, we can also say that this rate depends on the technology, because there is a constant alpha in the last formula that I showed you that does depend on the fiber that you're using. So for precise terms, we could go with both C and D. Okay, now we can, I guess, stop sharing. All right, and how do we actually solve this issue of exponential decrease with distance? Well, we can use something called a quantum repeater that uses quantum memories to help us establish entanglement across large distances. Okay, so let's imagine now that we have Alice, Bob, and an entity called a quantum repeater sitting in between Alice and Bob. Both of them are displaced by a distance L, and the repeater sits in the middle of the path connecting Alice to Bob, or the line connecting Alice to Bob. And we're going to assume that this repeater has two memories, 2 qubits in its registers, that it can use to generate entanglement with Alice and Bob. So the first thing that this repeater will do is essentially to create a Bell state with Alice and store one of its ends in one of the qubits in its registers. Then it will generate another Bell state with Bob. And once these 2 states are generated, the repeater will perform a very special type of measurement to propagate the entanglement that it has with Alice and Bob, or transform this entanglement into an end-to-end entanglement between Alice and Bob, right? And this can help us to overcome this exponential decay, because now the rate that we have between Alice and the repeater is e to the minus alpha L over 2, which is the same on the other end, meaning the rate that the repeater can create a Bell state with Bob. And we can generalize this idea to put as many repeaters as we would like between Alice and Bob, shown here in this figure on the bottom, such that we have a rate that depends on the length between Alice and Bob, but decays with the number of repeaters that are introduced between these 2 endpoints. This idea of adding quantum repeaters in between end nodes can be generalized into a quantum network. We can imagine now that we not only have repeaters that will connect only 2 end nodes, but quantum switches that have access to memories, and that will allow us to establish communication between multiple end nodes. We can imagine that these repeaters are interconnected with lossy links, that we can use these links to generate link level entanglement or link level Bell pairs, and that using this special type of measurement, the switches can concatenate entanglement and push or establish Bell states between end nodes of the network. And there are many challenges when thinking about or designing a quantum network. For instance, we need to decide if we want to perform entanglement distribution, meaning the process that I just described to you, or that essentially attempts to distribute entanglement between nodes and then use this entanglement, for instance, to perform teleportation, or if we want the network to support direct distribution of quantum or direct transfer of quantum information, meaning instead of distributing Bell states, we just use the fibers or the links to transmit qubit states from one node to another. Then we also need to be able to overcome noise, which is one of the major challenges in quantum technologies. We need to decide which user groups we're going to serve at a given time instant, in a similar way that the classical internet does, which leads to a plethora of problems in performance evaluation and resource allocation. Then we need to be able to perform network management, because it's very likely that once we start interconnecting the switches, creating a big network, we're going to see failures happening throughout the network, and it's important to be able to detect this failures. And finally, we need to be able to design data and control plane, meaning part of the operations that a network needs to do will be for control, or deciding which end nodes to serve, when to create a Bell state, right? And there's another part of the network that needs to be used to distribute or data, quantum information, essentially, between endpoints. And with this, we finalize the introduction. And now Don will talk to you about the similarity and differences between classical and quantum networks. I'm going to stop sharing.
Yeah. Thanks. So let me go ahead and share. Okay, can you see my screen? Thanks.
Yes, Don.
Okay, so in this section, what I want to do is I'm going to give sort of an overview of classical networks, and at the same time, an overview of a quantum network, and sort of compare and contrast as we go along. I'm going to start with a quick overview of the internet. Then I want to talk about network services and routing, talk a little bit about switch and router design, and as I said, compare and contrast as I go along. So first, let's start off with a nuts and bolts view of the internet. It's a network of networks. There are internet service providers, large ones, small ones. It connects home networks, mobile networks, public networks with private intranets. It's loosely hierarchical, and associated with it is a set of protocols which control sending and receiving of information. And I'm sure most of you are familiar with some of the protocols that I've listed there: TCP, IP, the Internet Protocol, HTTP for the web, Ethernet, Wi-Fi. It's sort of governed by a standards body called the Internet Engineering Task Force. And what they do is they end up putting out documents that are referred to as requests for comments that include sort of standards by which we sort of live with. There's a research arm to it, the Internet Research Task Force. And for those of you who are interested, there is actually a working group on the quantum internet. So let's look a little bit more. If we look at the network, we have at the network edge, we've got applications and hosts that are connected to a network core, which consists of routers. It's a network of networks, as I mentioned before. Also attached to it will be access networks, like a home network would be an example, or a wireless access network. And if we look at the network core, which is really sort of what we're interested in, let's say with respect to the quantum internet, it's a mesh of interconnected routers. And one of the fundamental questions associated with this is, how do you transfer data through the network? And there are two approaches that have been studied throughout the years. Circuit switching, which essentially came from telephony, and the idea there was to dedicate a circuit for, let's say, each call or each, let's say, flow within the network. And the other approach, which is what is commonly used in the internet, is packet switching. And here the idea is that data is essentially broken up into discrete chunks called packets, and then each of the packets is transmitted throughout the network, let's say from a transmitter to a receiver, or a web server to the client. So let's look at circuit switching first, and then packet switching. The idea with circuit switching is that you reserve resources end-to-end for calls. So this red call then would have resources reserved. Here we have another pair of users, let's say, that are involved in the call. And the kinds of resources that we're talking about would be link bandwidth. It would be switch capacity through each of the switches on the path. The resources would be completely dedicated to that call, which means that if the call was completely idle, those resources wouldn't be used for anything. And what you end up with is guaranteed performance, that often referred to as circuit life. And one of the things about this is that this kind of approach requires being able to set up calls. And that certainly, you know that from when you make a phone call, that there's a call setup that sort of takes place in while before you can actually start talking to the other party. Packet switching, here what we would do is we take the end-to-end data stream, divide it into packets. And so if we have two users, A and B, their packets would share the network resources. Neither of them would have resources dedicated to them. And each packet would use the full link bandwidth. And so here, the resources are used only as needed. Now, what this does is it introduces contention for resources, because users A and B may want resources at the same time. And so the aggregate resource demand could exceed the amount available. This can cause congestions, and the way that it's handled is that these packets then are sort of queued up, waiting to use a link. And so this gives rise to the store and forward paradigm, where packets move one hop at a time. They transmit over a link, and then they wait at the router for the next link. And so here's an example to sort of show you what the pros and cons are. Suppose we have 100 megabit per second link, as we have here, and each user requires 10 megabits per second when it's active. And each user is only active 10% of the time. If you were to allocate resources to the users according to circuit switching, then you could support 10 users. Okay, but of course, what would happen is that most of the time, the link would be idle. And so if you were to use packet switching, it turns out it's a very easy probability calculation to make. If you have 35 users, the probability that more than 10 of them would be active is less than 0.0004. And so what that means is that there's a very, very high probability that users will not notice any contention for the link among those 35. And so what you should take away from this is that packet switching will allow more users to use the network. And so we have a poll question here. Has to do with packet switching, and the choices are the following. A is that with packet switching, you have to make a connection between endpoints before communication starts. B is that under packet switching, the users share the bandwidth of the channels all the time. C, that the amount of bandwidth that's available to a user is inversely proportional to the number of active users. And D is that packets use the entire bandwidth of the channel when they're transmitted. And E is just, I don't know. Yep. Okay, half of you have given answers. It doesn't look like more of you will. So it's not A, because in packet switching, there's no notion of, let's say, doing a call setup. So you don't have to like set things up ahead of time. B is not the right answer because users, what will happen is that when a user's packet goes into the channel, it will hold all of the bandwidth of that channel until the packet is transmitted. Okay. And C, I guess C is a little ambiguous, but again, there's no sharing at any one point in time of bandwidth among the users. They're sharing over time, but what happens is that whenever the packet belonging to a user gets the channel, then it gets the entire bandwidth until the packet is completely transmitted. Okay, so let's talk a little bit more about internet. I mentioned that it's a network of networks. You can think of it as sort of hierarchical. What you have at the center are what are referred to as tier one internet service providers, ISPs like Verizon or Comcast or AT&T. They tend to have national or international coverage, and they will treat each other as equals. And so they will interconnect with each other sort of privately, and that will have some kind of contract by which they sort of allow each other to use each other's network as needed to be able to serve transit traffic. You then have tier two ISPs, sort of at the next level of the hierarchy. They're smaller, often they're regional, and they will connect to one or more tier one ISPs and possibly to other tier two ISPs. And the main thing about them is their relationship with a tier one ISP is really as a customer to a tier one provider. And so the tier two ISP will pay the tier one ISP for connectivity to the rest of the internet. And then you'll have tier three ISPs, you'll have the local ISPs that, let's say, customers or users are connected to, and they're sort of like the last hop access network closest to the end systems. And these ISPs are customers to higher tier ISPs, either tier two or tier one, which connect them to the rest of the internet. And what's really interesting about this is that a packet ends up passing through many, many networks. And you can check this out by doing a trace route. And it's unbelievable. You could go through like 4, 5, 6 networks. Now, we talked about protocols, and there is what's referred to as the Internet Protocol Stack. It's a layered sort of way of describing the Internet architecture. At the top, you have application protocols that support network applications, HTTP being an example, SCP, which is secure copy, would be another example. Below that, you have the protocols that essentially govern data transfer between hosts. TCP and UDP are the most commonly used here. Below that, you have a network layer with protocols dealing with the routing of packets from source to destination. The sort of famous IP Internet Protocol falls there, as well as routing protocols. The links connecting routers have their own data transfer protocol describing or governing how data navigates between them. And then you have at the bottom layer a physical layer where the protocol describes how bits are placed on the wire. So with that, let's touch base with quantum networks. And just quickly, Matheus went through this. Quantum networks are going to be tough because quantum communications is hard, because of the fact that you have a decay in an exponential decay in the transmission rate as a function of distance. And unfortunately, the no-cloning theorem precludes copy and amplification. And as we saw before, what is being pursued as a solution to this is to have what are called repeaters with quantum memories. And the way that they would work is they would be used to set up Bell states or Bell pairs between themselves and, let's say, end nodes or other repeaters. And then they would perform swaps, which would be a way of promoting the entanglement. And what that ends up sort of decreasing the exponent in that rate function, so that it's proportional to half of the distance between Alice and Bob. And you can sort of take that to the extreme where you would place lots of repeaters and you would get a much, much larger transmission rate. Okay, so you have this repeater chain, and if you have lots of memory repeaters, then you're able to generate a distance-independent entanglement rate. Okay, and you do that because you're able to essentially get an exponent that is independent of the distance. But I want to just mention something that I'll come back to later on. This distance independence is for the case where these swap operations that essentially, let's say, propagate the Bell pairs or the entanglement always succeed. And unfortunately, not all technologies allow that. I should mention, if you only have one memory per link in each of these repeaters, then you still end up with an exponential decay. Okay, that as the distance between the end nodes increases, you get an exponential decay. So this distance independence that I mentioned before really comes from the fact that these repeaters are going to have lots of memories to be able to store Bell pairs. Okay, associated with a quantum network, there are already some proposals for what the protocol stack might look like. And sort of analogous to the internet protocol stack, you'd have an application layer. The protocols there would support network applications like quantum key distribution or remote sensing or distributed quantum computing. Below that, you'd have a transport layer, and that would be concerned with, let's say, data transfer between hosts. And I've listed QTCP, UDP, but really tongue-in-cheek. They don't exist yet, but I think eventually there will be the equivalent of TCP and UDP. Below that, you have protocols at the network layer, and they're going to be concerned with how to generate bell pairs between end nodes. And that's going to be concerned with how do you do path selection through the network and something the equivalent of, let's say, a quantum IP. At the link layer, you'll have link level entanglement generation. And then at the physical layers, it's going to be photon qubits on the wire. I'd like to talk just a little bit about reliable communications to contrast what we do in the classical network with what the challenges are in a quantum network. In the classical network, the errors that we have to deal with could be bit flips, could be erasures. The most prevalent error is a packet that's dropped at a router. And so the recovery schemes that have been proposed, well, they're to do error detection and error correction. And in the case of handling dropped packets, to do packet retransmission. And that's really the mechanism that TCP uses, for example. And I just want to point out that that mechanism relies on cloning, that you be able to make a copy of the packet so that you can retransmit it later. And on the right is just sort of a diagram of a recovery scheme like that. You have the sender sending a packet 0, the receiver receives it, it sends an acknowledgement back for that packet. Sender sends packet 1, it gets lost. Typically, the sender will have a timer associated with each packet. When it goes off, then it just resends the packet. And of course, it can resend it because it was able to clone it. In quantum, there are a number of challenges that we have to worry about. One is that qubits are not self-protected against small perturbations. When Matheus sort of talked a little bit about quantum, okay, well, in the classical world, we have zeros and ones, we encode them. And if the encodings deviate a little bit from what they're supposed to be, they're usually close enough that we know how to, which one it should correspond to. But in the quantum world, qubits can take an infinite number of states that are essentially linear combinations of zeros and ones. And so if the state deviates from what it should be, we don't know if it's that it's an illegitimate state. It may be legitimate, and so we don't really know how to restore it. And so that requires like a really sophisticated error correction codes. The other thing is when you place qubits in memory, they have limited coherence time. So you may place it in memory as, let's say, a qubit with state 1, and as time goes on, it starts to deviate to 0. And so you have decoherence that takes place that has to be dealt with. So what has been proposed is what's called entanglement distillation, where what you do is you start off with, let's say, several bell pairs. They may not be imperfect. You essentially perform some operations on them, do measurements with the goal that at the end, you'll be left with one very, very high quality bell pair. And there's a very, very simple circuit for doing that I'm not really going to go through, where you take two bell pairs, I'll call one a source, one a target, perform what's called a C0 at both Alice and Bob, and then Alice and Bob measure the target pair. They send the results to each other, and then they can decide whether they're left with a better quality pair than before. The metric that's typically used here is what's referred to as fidelity. And think of it as a measure of closeness of entanglement to perfection. If the fidelity is 1, it's perfect. And as it decreases, it's deviating from what it should be. When you perform distillation, the distillation is probabilistic. It succeeds with some probability P sub S. And here I have a plot sort of indicating the following. Suppose you have two bell pairs and with initial fidelity, let's say given on the x-axis, 1/2 to 1. When you distill them, if it succeeds, you'll get a final fidelity that will be higher than what it was initially. However, this red curve indicates the probability of success, and so it may fail. So suppose the initial fidelities were 0.7. It succeeds with about a probability of 0.6, but when it does, the fidelity becomes 0.85. So with that in mind, let's go back to this linear repeater network that we talked about before. Typically, the links consist of what are referred to as modes. Think of a mode is that you could have several frequencies, or with photons, there are different ways you can polarize the qubits. Or you could do sort of like time multiplexing, and each bin in the multiplex interval could be thought of as a mode. And so what you do then is at one instance, you attempt to generate bell pairs between successive repeaters on each of the modes. Some of them succeed, some fail. If the probability of success for a mode is P0, then the probability that you'll get at least one is given by this expression right here. And so what this does is it increases the link success probability, P, so that it's larger than P0. But the other thing is if you have a number of the modes have succeeded, you have an opportunity to do distillation. And so you might have a situation here where on this link, we have two bell pairs, each of them with some fidelity F0. We can distill, and we will then end up with bell pairs with higher fidelity. And so this brings up interesting questions about when and how much should you distill? Should you distill across single or multiple links? And suppose that Alice and Bob have a minimum end-to-end fidelity constraint, then how would you provide that? So with that, let's go to another poll question here. Matheus, could you, thanks. So let me just walk you through. What's the purpose of distillation? Is it to increase the bell pair generation rate, increase the fidelity, increase the distance by which you can do entanglement distribution, or decrease fidelity so as to increase rate? Or, E if you're not sure what the answer is. Okay, so I think most of you understood what the purpose of bell pair of distillation is. It takes two or more bell pairs, and at the end, it produces, if it succeeds, it produces one that has a higher fidelity than any of the ones that were, let's say, used in the process. Okay, so let's come back to classical networks. I want to talk a little bit about network layer function. Basically, it's concerned with transporting a packet from a sending to receiving host. The network layer protocols reside in every host and router. And there are three important functions. One is selecting a path that the packets will take. A second is switching, that at each router we have to decide how or where to move packets from, let's say, input to appropriate router output. And then with some architectures, may be necessary to do a call setup. And also associated with the network is the network is going to provide services to the users. And so an important question is, what's the right service model for the channel transporting packets from a sender to a receiver? Okay, should it be that it guarantees some amount of bandwidth, or should it be concerned with maybe preserving inter-packet timing, trying to minimize jitter? Or should it be concerned with loss-free delivery, in-order delivery? Should it worry about, let's say, providing congestion feedback to the sender? And it turns out in the current internet, the most important abstraction that's provided by the network layer, it's really, should it be virtual circuit or should it be datagram? And so let's talk about both of these, starting with virtual circuit. And virtual circuit, you can think of it that the source to the destination path behaves like a telephone circuit. It's still using packets, but it's trying to make it look as if it were a telephone circuit in terms of performance and in terms of network actions. And so this is going to require a call setup or teardown before data can flow. Each packet is going to carry a virtual circuit identifier, identifying which VC it belongs to. Every router on the source destination path is going to maintain state for each virtual circuit. And it's possible that some link and router resources may be allocated to the virtual circuit as a way to really be able to ensure that the application or the flow gets circuit-like performance. So here's just an animation showing it. We initiate a call through the network. It's incoming to the destination. Destination, let's say, will accept it and the network will accept it. So the call will become connected and then data can flow from the sender to the receiver. In a datagram network, which is the internet model, there's no call set up at the network layer. No state is maintained at the routers about end-to-end connections. There's no network level concept of a connection. And the packets are typically routed just using the destination host ID. And what that means is that packets between the same source destination pair may take different paths. So let's look at the quantum network and the same question in terms of service model. Okay, what service model should a quantum network provide between two quantum nodes? You know, should it guarantee rate, a latency guarantee, a minimum fidelity guarantee? And this is sort of the crucial question. And again, this is going to be the most important abstraction that's provided by the network layer. And it looks like what is going to come out of this is that there are going to be two sort of possible services that are being considered. One is that the network, let's say, it generates and distributes entanglement to users, or the second is that the network essentially is used to transmit quantum information from one node to another. Okay, we've really sort of talked about entanglement distribution before, but again, just to remind you, this is referred to as also as a two-way network architecture. And basically, the idea is that you create and distribute bell pairs or entanglement between users. And then if the users want to transmit information to each other, they can then use teleportation, which Matheus covered in the first part of this. And so this service is going to rely heavily on the use of distillation to handle noise. Distillation to improve the quality of the bell pairs that the end users use, let's say, for teleportation. And it's called a two-way network architecture because when a repeater does a bell swap, it generates some classical information that's required by the end nodes to correct their qubits to ensure that, let's say, the two end nodes end up with the bell pair that they want. And so that brings us to the next poll question, having to do with quantum teleportation. And the choices here is you use teleportation to correct errors when distributing bell pairs. The other is that you use it to transport classical information from one user to another through the expenditure of a bell pair. Or you use it to transport quantum information from one user to another through the expenditure of a bell pair. Or that you can use it to transport a human being from a spaceship to a planet. Okay, so most of you have responded, and most of you remembered that it's really used to transport quantum information, and it requires a bell pair as sort of the resource in order to do that. What's interesting is there is another sort of end-to-end quantum operation that corresponds to B, but quantum teleportation is not that. Okay. So going back, the other service could be quantum information transfer. It's often referred to as one-way network architecture. And basically here, you just transfer the quantum information directly through the network. And, you know, note the resemblance to a classical network. And this relies heavily on quantum error correction. If you want to transmit one qubit, you may have to encode it into like 100 or even hundreds of physical qubits in order to be able to correct at the end. And the other thing to be aware of is that it doesn't require any exchange of classical information. And that's why it's referred to as a one-way architecture. And I just want to point out the services are interchangeable, that you could have the end node generate a bell pair, keep one of the qubits, and then use this quantum information transfer service to send the other qubit to the other node, and then it would be as if they had generated, the network had generated and distributed the bell pair. Okay, so what we imagine is eventually the quantum internet is going to consist of lots of quantum networks, and quantum information will pass through many of them or perform end-to-end entanglement over many networks. The networks could have different kinds of quantum technologies. Some internet service providers will distribute entanglement, others will transmit quantum information, and you'll need a quantum internet protocol to sort of glue everything together. So before we move on, so the pros for two-way is that in order to deal with noise, it uses distillation, which is much simpler than quantum error correction. Bell pairs are fungible, which turns out to be particularly useful because it means that you can sort of pre-share entanglement. It doesn't matter what bell pair you use. And because they're fungible, you can generate high rates, and it tolerates noisy gates. The cons are that you have to use classical communications, and it increases latency, and you need to be able to store bell pairs at the intermediate repeaters, and so it has a high memory requirement. With one-way, the pros are that you don't need any classical communications. You need very little in the way of memories, but the cons are that it relies on quantum error correction, which is very challenging and requires very high quality gates, lots of qubits. And that brings us to the next poll question, which are, what are the advantages of a two-way quantum network architecture? And, select all that apply. It can tolerate noisy gates. It will introduce latencies due to the need for classical communications. Requires quantum memory at switches. It can provide high rates. Or if you're not sure, you can mark E. Okay, so most of you have responded, and as I mentioned earlier, it can tolerate noisy quantum gates better than one-way quantum network architectures. And it can provide high rates because of the fungibility of the bell pairs. I would say B and C would not be advantages, although they are certainly properties of the two-way quantum network. So A and D are sort of what I was looking for. Okay. Just say a little bit about routing. The goal with routing is that we want to determine a good path through the network from source to destination. And typically, we do this, we think of it as a graph problem, where the graph consists of routers as nodes and edges are the physical links. There are costs associated with the links. There could be delays, or could be something related to the bandwidth or cost. And a good path typically means a minimum cost path, although there are other definitions possible. And Dijkstra's algorithm is really sort of the canonical algorithm for computing routes. Well, just say a little bit about how routing algorithms are classified. There's a question of whether they're global or do they use decentralized information. A global routing algorithm, you'd have a central controller that has complete topology information. In a decentralized approach, routers might exchange information with each other and run some sort of iterative algorithm. Algorithms could be static or dynamic. And by static, I mean that routes change very slowly over time. Dynamic, that the routes change more quickly, perhaps because of rapid changes in the network structure. And the current approach in the classical internet is sort of to have a logical central controller that has complete information. Currently, there are other constraints that come up, like policy constraints. ISP8 doesn't want its traffic carried by SPC, or prefers it to be carried by SPB. Worry about calculating backup paths. Take advantage of diversity for load balancing. And I would say the quantum routing, that most of the work has been on developing static algorithms, and they typically are shortest paths with link costs. The link costs might be the inverse of the entanglement rate. It could be the link fidelity and others. And there are a fair number of papers that have been developed along these lines. Just a little bit more, I want to say a little bit about classical routers. Classical routers have two functions. They run a routing algorithm, or a routing protocol for choosing, let's say, paths. And then they're responsible, of course, for forwarding packets from incoming to outgoing links. Just to contrast with a quantum switch would have a bunch of quantum memories, which would be used for loading bell pairs that are being generated across the links, and for doing measurements that would be needed for swaps. You would have some quantum logic across the qubits that are held in the quantum memories. You'd have a bunch of multi-photon entanglement sources to be able to generate entanglement at the switch, and then some classical computing and classical communications capabilities. Okay, and so the challenges here that come up is what the switch design oops, sorry, let me, yeah. There still are questions about how to design the switch, how to, let's say, do teleportation. We're going to be concerned in the second part of this on, what's the capacity of the network? How do you do resource allocation? Interesting questions that come up with respect to path selection is, do you use global information, or can you get by with local information? And all of this seems to point to the use of circuit switching or virtual circuit switching in the context of a quantum memory. Another big challenge has to do with dealing with memory decoherence and with gate errors, and we'll talk a little bit about that later on. as I said earlier, the quality of information, one metric for that is fidelity, which degrades over time. And so it brings up questions about if you're trying to schedule, let's say, bell pair creation or teleportation of qubit, what should you use as the criteria for picking qubits? And we'll address this later on as well. So just to sort of summarize this, I hope to give you sort of a flavor of what a quantum network looks like in comparison with a classical network. The entanglement distribution service is very different from a quantum information transfer service. And it, to me, suggests that there are some, very exciting opportunities for sort of doing design and engineering of an entanglement distribution network. Quantum networks seem to introduce new problems, but also a lot of problems that were already present in classical networks appear, but with sort of interesting wrinkles. And then there are all questions about how you do resource allocation, path selection, scheduling, and how to deliver quality of service in a very noisy environment. And so I'll stop here. And I think what we should do is, let's say, take we can answer some questions, but take let's say, a 5-minute break. And let's say reconvene. It's 4:15 my local time, so let's say at 4:20.
Okay, so I guess now we can restart, and we're gonna talk about network management and quantum network tomography in particular. Now that Don had discussed with you all the connections and similarities and differences between classical and quantum networks, quantum network tomography is one topic in quantum networks that that has started from the classical version of a network tomography. Okay, so for an outline of this part of the talk, I'm going to introduce to you what network management means and give you a brief overview on classical network tomography. Then we're going to go to quantum network tomography. We're going to define to you the problem that quantum network tomography addresses. And finally, we're going to review some of the results that have been obtained for star networks and how we can characterize star networks formed by flip channels. Okay, so essentially, network management is the field that attempts to collect information from the network and provide this information for managers to be able to find faulty hardware and that can somehow probe how the internet is the networks are behaves and what is necessary for to fix issues that are being experienced by users. So essentially, we want information to aid decision making by network managers, and we can do things such as determining the traffic patterns, the communication patterns that the end nodes exhibit at a given moment in time. And network tomography is a subfield of network management with the goal of inferring the internal behavior of the network from measurements performed by the end nodes of the network, the external nodes, which essentially translates to the estimation of error parameters for internal components of a network from end-to-end measurements. And the goal of network tomography is to obtain what we call identifiability, that is, obtaining a particular one value of parameters from a set of observations that can help us identify the behavior, the instantaneous behavior of the components from this end-to-end measurement. For instance, network tomography may attempt to characterize the delay being introduced by each one of the links of a network when end nodes are using the network to communicate, and identifiability would translate to being able to specify a single value for the delay of each of the links in a path, for instance, connecting to end nodes. And why do we want to do this in an end-to-end way? Well, end-to-end measurements require no participation by the network besides the service being provided by the network. In some sense, this measurement that we perform is implemented by regular packets that are used by the end nodes to exchange information. There is no administrative access required for the end nodes to perform this characterization, because they don't need to probe or to query directly the network hardware for measurements. We can perform inference across multiple domains in the network. As Don explained to you before, the internet is a very complex system formed by multiple networks, and performing end-to-end estimation allow users to estimate performance across multiple domains. There's essentially no cooperation required from the network infrastructure for the end nodes to perform measurements in an end-to-end fashion. And this sort of techniques can be used to monitor agreements in the service level. So two ISPs, for instance, may have an agreement that they will provide some particular service to each other, and network tomography can help these ISPs to monitor if this service is being provided in the way it should. In addition, end-to-end characterization enables reconfigurable applications at the end nodes, for instance, such as the transmission of video, of audio, and you can perform reliable multicast communication between end nodes by characterizing the performance of the network at a given time instant and modifying application behavior based on estimates for the error parameters of the network. So now let's go with a simple poll question that is, why end-to-end estimation is interesting. So for A, we have, it does not require administrative access. B, yields reconfigurable applications. C, does not require trust in the infrastructure. Or D, all of the above. Okay, I think we have, yes, we read. Okay, cool. So yeah, as most of you pointed out, all of the answers in this here are correct. It really does not require administrative access because it's performed by end-to-end measurements. You use reconfigurable applications because the end nodes will have a description for the behavior of the network from the measurements, and does not require trust in infrastructure because the end nodes use the network for the service that it is provided to them. Okay, so let's continue. Let's go over some definitions. Link level metrics are essentially what network tomography is trying to estimate. And you can imagine that link level metrics are delay introduced by a link, the loss probability of the link losing, let's say, a packet or a bit, or the bit flip rate introduced by that link when this link is used for communications. Unicast communication is a model of communication where one end node communicates with another end node in a pairwise fashion. For instance, A may want to communicate with B, sending a message here depicted by these red arrows. And A also may want to communicate with C and send a different message depicted here by these purple arrows. There is multicast communication, which is a one-to-many paradigm of communication let's say, imagine now that A wants to send a message to B and C, and this message is the same. And multicast allows us to do this in the following way. A sends this message to S, then S duplicates the message and sends one copy to B and one copy to C. And what we mean by estimation here is essentially the end nodes of this network, A, B, and C, will perform measurements. Let's say compute what was the total delay introduced by these two links on the message that A sent to B, and a delay introduced by these two links and the message that A sent to C, and then send this messages to a fusion center in the network, which can be any node, even a node that did not participate on the communication, which can then be used to estimate the values for each one of the link metrics of interest. And unicast tomography works in this particular way. Well, we have some assumptions. Let's assume that the links are symmetric, meaning that the behavior we want to estimate for each one of these links is the same if we use the link from A to, let's say, this intermediate node, or this intermediate node to A. And we're going to assume that these metrics that we want to estimate are also additive, meaning that if we use the links interconnecting A to B, the metric, the end-to-end metric, is the sum of the metric characterizing the link from A to this intermediate node, and then the metric characterizing the link from the intermediate node to B, which we show here is R0 and R1. So then what we can do to, let's say, estimate this metrics for each one of these links is as follows. We're going to send a probe from A to B, right? And this will allow us to measure the sum of R0 and R1, which we represent here as RAB. And we can send a probe from A to C, which will allow us to measure a different sum now, the sum of R0 and R2. And finally, we can send a probe from B to C, which allows us to measure the sum between R1 and R2. And now, the end-to-end measurements, which we show here as the left-hand side, are values that we have after we perform the communication between the end nodes. And these three equations form a system of linear equations which you can solve to compute R0, R1, and R2. And we call this system in the unicast tomography case of a routing matrix, because these sums actually represent routes that we use to send messages between the end nodes. And we can identify the parameters, in this case, find a single solution for a system if our routing matrix, which is represented here by the right-hand side of this equation, is invertible. Meaning if each one of these equations is linearly independent. And this is in general true for generic trees. I just showed you here a very simple star network that we use unicast tomography to characterize. And in fact, we can use this idea to obtain solutions for additive metrics in general graphs. So if you want a bit more of a concrete example on what we're inferring here, imagine that these R's are delays introduced by the links. And with this notion of sending information across the network in a particular way, we are able to compute estimates for each one of these values. And one thing that we did here is if we can have measurements performed on cycles in the network, we can actually characterize, identify the parameters for all links using a very simple technique. Okay, so now let's go over a simple question here. What is a sufficient condition for link identifiability through unicast tomography? We have A, link asymmetry, B, link symmetry, C, invertibility of the routing matrix, or C, having a star network topology? Or E, I don't know. Okay, so I guess we got most of the answers. And I think that, yeah, most people select the correct answer. That is the invertibility of the routing matrix. Yeah, we did assume that the links were symmetric, but that was just an assumption to simplify the description of unicast tomography. And we did look at a very simple network, meaning a network with a star topology, but a sufficient condition for identifiability is invertibility of the routing matrix, because we can, if the routing matrix is invertible, we are able to solve that linear system and find a single solution for the parameters, no matter what type of underlying assumptions we have. Okay, so now let's continue and look at multicast tomography, which will be very useful when we talk about quantum network tomography. Let's imagine once more that we have a very simple star network connecting a source with some receivers, in this case, a single source with 2 receivers. And a star network is a very simple tree because there are no cycles within this topology. And a multicast protocol to send messages between the source and the receivers are similarly to what I explained before. The source can send the message to the intermediate node, which can then duplicate this message and send one copy to each one of the receivers. So the probes essentially are copied in multicast communication as necessary, meaning there is, in this case, only one copy of the message that traverses each one of the links, and this copy is created, and the message sent from the source to the receivers is duplicated at the switch only. And what ends up happening with this notion of only copying as necessary is that the receivers observe a correlated performance. And the idea in multicast tomography is essentially to exploit the correlation introduced by this copying procedure to estimate loss rates and delays. Okay, so now let's imagine that alpha is the probability, alpha sub I is the probability that a bit sent from between each one of these links, that this bit will survive in the communication procedure. Essentially, is a probability that the bit will be received at the other end of the link once communication is performed. And let's imagine that the source will send to the end nodes a probe passing by the intermediate node. And if everything works correctly, both receivers will receive the message. But if the message correctly reaches the intermediate node, and the message may fail, or the transmission may fail from the intermediate node to the receiver on the left and be received by the receiver on the right. Or we can have the opposite scenario where the receiver on the left does receive the message and the receiver on the right does not. In this case, these events allow us to estimate these probabilities and, in fact, to identify the loss rate for each one of these links. Okay, so now let's go over a poll question concerning multicast tomography. That is, what is the key principle behind identifiability in multicast? Okay. So A, we have metric correlation in common links in the multicast tree. B is invertibility of routing matrix. C is link symmetry. And D is link asymmetry. We have majority of responses. And the answer is metric correlation in common links in the multicast tree. You can think about invertibility of routing matrix in this case, but that's not really the fundamental principle we explored. And assuming that the links are symmetric, may make the problem easier for some particular scenarios, but in general, this is not the fundamental principle explored here. All right, so let's now shift gears to talk about quantum network tomography. Before we had a classical network, and now we have a quantum network, and we can assume that this quantum network is formed by multiple nodes. We might have some ground stations, some free space quantum switches that all together are enabling n nodes, which you show here as this blue computers, to exchange quantum information among themselves. And the fundamental question we want to address in quantum network tomography is how to characterize the links in this network performing end-to-end measurements. And the idea is that the n nodes are able to perform quantum circuits. They can request a network to perform state distribution, meaning they can request a network to perform entanglement quantum circuits for the intermediate nodes to execute. And in turn, the intermediate nodes can receive requests for circuits to be implemented. They have access to some ancilla qubits that they can use to help the procedure of establishing end-to-end entanglement, but they are not allowed to perform quantum measurements for estimation. And the motivation behind quantum network tomography is that we can expect that quantum networks will be formed by inhomogeneous quantum hardware. You can imagine we're going to have some, as I said, ground stations, some free space quantum switches that are, and the links between the free space links and the ground station links are completely different, and they probably will introduce different noise and errors to the information being transmitted. We might have hybrid communication media. Again, we might have switches formed by different physical platforms, and each physical platform will introduce its own sort of errors to the information being transmitted. It's very important to perform network management once we have large networks. Quantum network tomography will help to perform the detection of faulty network hardware by maintaining a description of the behavior of the network performed through end-to-end measurements. And it can even help decision-making in resource utilization, for instance, in routing by utilizing the description for the noise in the quantum channels to select a next hop, for instance, in a routing protocol. A very interesting thing that quantum network tomography enables for n nodes is to perform reconfigurable applications, such as noise-informed quantum error correction. For instance, the nodes might be communicating at a particular rate, and they might decide which encoding and decoding, quantum error correction encoding and decoding protocols they will use based on estimates for the current behavior of the network. A very interesting thing that quantum network tomography also allows us to do is quality assurance. Imagine that we pay for a quantum network service, and by performing quantum network tomography, we can validate if the service we're paying for is actually the service that is provided to us. And the transition from classical network tomography to quantum network tomography goes as follows. In classical, we have link level metrics, which were, for instance, loss and delay introduced by links. And in quantum network tomography, we have quantum channel parameters, meaning parameters that can specify the precise transformation that the quantum channels are performing in the information being transmitted. We had probes in classical networks that were packets sent by nodes. And in quantum, we're going to do state distribution, which translates to generating entanglement between n nodes to perform measurements. We had in classical unicast communication, and in quantum, this becomes bipartite state distribution. We had multicast in classical, which becomes in quantum multipartite state distribution, for instance, distributing a GHZ state. And in classical, we had end-to-end measurements. And in quantum, we have quantum measurements performed in the end nodes. Okay, so let me just cover a very briefly, mixed states, which is a fundamental mathematical background we need to understand quantum network tomography. Pure states are states that describe closed quantum systems, and we really represent pure states through the norm vectors in Hilbert spaces. But mixed states are slightly different than pure states. They really represent a statistical ensemble of quantum states. For instance, we might have a qubit preparation device that whenever we use that device, it prepares a state 0 with probability 60% and a state plus with probability 40%. And mixed states are efficiently represented by density matrices. So to give you a depiction of what I mean by a mixed state, let's imagine we have a source, and every time we press a button, the source produces a state psi. And there may be some particularities of the source that the state psi is not actually always the same pure state, but is, as I said, let's say a mixture of 60% of the state 0 and 40% of state plus. And the way you represent this efficiently is through a matrix, which is a density matrix, characterizing this mixture of this ensemble of quantum states. Okay, so let's imagine we have one qubit. And if we have a state psi of this single qubit, it lives in a two-dimensional Hilbert space. And the matrix formed by the outer product of this state psi with itself is a projector of this space that projects vectors into the vector psi. If we have a mixed state rho, this mixed state maps this bidimensional Hilbert space to itself, and we can describe this mixed state with a summation over pure states, as I show here in this equation, where psi k is a pure state, and pk is a probability associated with that pure state. Density matrices are Hermitian and positive semi-definite and have unit trace. Okay, so let's imagine that we had that preparation device again, that qubit preparation device that produces 0 with probability 60% and plus probability 40%. Then the projector for 0 is this matrix 1, 0, 0, 0. And the projector for plus is the matrix 1, 1, 1, 1 times 1/2. And when we use this rule to compute the density matrix associated with this mixed state, we have this density matrix here, 0.8 and in this first element and 0.2 in the other three elements. All right, and now that we know how we can represent mixed states, we can talk about the transformations that quantum channels perform in mixed states. So let's assume that we have two network nodes and that we have a link interconnecting these two nodes. And this link represents to us a quantum channel that will transform a qubit sent through this link. And so for every link in the given network, we're going to assume that this link is a Pauli channel, which is a very particular type of quantum channels described by Pauli operators. Where here, rho is a density matrix, and sigma k is a given Pauli operator, one among the 4 Pauli operators defined for one qubit. And the restriction for our quantum channel in this case is that the thetas, which represent for us probabilities, that they must sum to 1. So what you can imagine that what this description tells you is that with a given probability, theta sub ek, once you send a qubit through link E, the outcome is the qubit that you sent, represented by rho, transformed by one of the 4 Pauli operators. And this is the thetas gives you exactly the probability that one of the Paulis will be applied to your qubit. So let's go over some examples to have a better intuition on what this mathematical representation means. We can have a bit flip channel described. A bit flip channel is one type of a Pauli channel. And a bit flip channel maps the state 0 to the state 1 and vice versa. And we can represent this bit flip channel with a formula here through this equation, where theta 1 minus theta e gives us the probability that a flip will occur once we send a qubit through that channel. We can have a phase flip channel that maps the state plus to state minus and vice versa. And it is very similar to the bit flip, but the difference is in the Pauli operator that can be applied once you send a qubit through the channel. Before we had the Pauli operator X, and now we have the Pauli operator Z. We can also have a channel that performs both a bit and a phase flip with different probabilities, which we show here with this particular equation. And for simplicity, what we're going to do is to focus on the bit flip case and understand quantum network tomography under the assumption that the links in our network are bit flip channels. Okay, again, let's recap what do we assume that the nodes can do. We assume that the n nodes V sub e of the network can perform quantum circuits, that they can request the network to distribute states for them, and that they can even specify for each node in the network being used to distribute a given request, the circuit, the quantum circuit that intermediate node must implement when it's distributing the state. And for the intermediate nodes, we're going to assume that they can receive requests for circuits, meaning the n nodes can ask them to perform specific quantum circuits to serve a given request, that they have access to some ancilla qubits. But we don't allow intermediate nodes to perform quantum measurements for the purpose of estimation. And our quantum network model, when we put all of this together, is as follows. We're going to assume that the network is a graph, where the vertices of this graph represent quantum processors, and the links in this graph represent quantum channels that can be either fiber optics or free space channels. We're going to assume that we split the network into end and intermediate nodes. The end nodes in this case are nodes A, B, C, D, and E. And the intermediate nodes are nodes F, J, K, and L. And we're going to also assume that these channels interconnecting all these nodes can all be modeled as single qubit quantum channels, in particular single qubit Pauli channels. And that our goal is to estimate the probabilities that characterize each one of these Pauli channels in a given network. For simplicity, we're also going to consider that we're doing one-way quantum transmission, meaning the protocols that I'm going to describe to you are really not trying to just are using links to send quantum information directly instead of performing or generating entangled states between nodes and then performing entanglement swapping to propagate entanglement towards the end nodes. They are simply used to send qubits between nodes directly. Everything that I tell you from now on is easily generalizable to two-way quantum networks, where we do use the channels to generate link level entanglement. But for simplicity of exposition, it's easier to discuss quantum network tomography considering one-way quantum transmission. Okay, so let me give you a very precise definition of the problem in mathematical terms. Our input is a graph. We have the node partition that tells us what are the end nodes and what are the intermediate nodes. And the output for our problem is an estimator, theta hat of E, for each link, E, in the network of the probabilities that characterize the underlying Pauli channels in this network. And the constraint is that the measurements, the quantum measurements we can use for estimation can only be performed at the end nodes of this network. And what we're going to do is to cast the quantum network tomography as a problem of quantum estimation. So to do this, we will need to perform parametrization, which means to use the network and distribute quantum states among the n nodes, such that the states depend on the parameters that we want to estimate, the parameters theta that we want to estimate. And I am just using the row of theta to denote here a mixed state distributed between the n nodes that depends on the parameters to be estimated. Then we're going to do some measurements at the n nodes on each distributed state, and the measurement outcomes will depend on the parameters that are trying to estimate, because the statistical mixture that we distribute depends on the parameters we're trying to estimate. Then the final step of this process is really to compute an estimator that tells us what are the, let's say, the Pauli probabilities for each one of the channels in the network. And as I said before, we can simply imagine that we send the classical results from these quantum measurements at the n nodes to a common node in the network, what I'm calling a data fusion center in the network, so that this node can use all the information from the n nodes to solve an inverse problem and obtain the estimator that we want. Let's dive a bit deeper into parameterization and how we can actually distribute a state whose measurements depend statistical give us outcomes that depend on the parameters we're trying to estimate. Well, what I mean by state distribution is really, in this case, the preparation of a given quantum state in the n nodes through the network. And let's imagine, for simplicity, that we have this 3-node network where R and L will generate an entangled state, or will distribute a state between themselves. So again, for simplicity, let's imagine that these links represent bit flips, and that 1 minus theta e is a probability for each one of these links that a flip will occur. So let's imagine that R prepares a state rho sub 0, which is just a pure state 0. It will send this qubit through the intermediate node. Recall that we are assuming one-way quantum communication. We're sending the qubit directly through the channel. The qubit that is received by this intermediate node is actually in a mixed state, theta 0, 0, plus 1 minus theta 1, 1, which means that with probability theta 0, if we perform a z-basis measurement on this qubit, we'll see state 0. With probability 1 minus theta 0, we'll see state 1. Then the intermediate node will forward the state to node L, and the mixed state describing this qubit here received by L has this form, right? Where it's 0 with probability theta 0 times theta 1 plus 1 minus theta 0 times 1 minus theta 1, and 1 with the probability 1 minus that. Again, what I mean by is 0 is if we perform a z-basis measurement on this state rho 2, we'll see 0 with this probability, and see 1 with 1 minus that probability, which is shown here by this equation. Okay, so to see how we can actually use parameterization to estimate these parameters, we're going to take another simplifying assumption and focus on star networks. So again, a star network is just a network formed by an intermediate node that interconnects n nodes. And we're going to assume that each one of these channels is a bit flip channel, which is described here. And our goal is to estimate the bit flip probability, or in this case, the probability of not flipping a bit for each one of these links when we are not allowed to perform measurements in the intermediate node. Again, for simplicity, we're going to focus on the case of a star with 3 n nodes. And the methods here really are applicable to stars with as many nodes as you may think of. Okay, and what we're going to do is to try to replicate the multicast communication protocol in the in this case a quantum network. Again, we have a 4-node star. We're going to select a node in this star to be the root of communication, meaning the node that will start the state distribution. For instance, let's assume we have node V0 to be the root. And then node V0 will prepare a qubit in state 0, as we see here. It will send this qubit, to the intermediate node V3, okay, which will receive this qubit, and it will apply a C0 controlled by the qubit that it received with a brand new ancilla initialized in state 0. Then it will V3 will just send one qubit that comes out of the circuit to node V1 and another qubit to node V2. V1 and V2 will perform qubit measurements in the Z basis. And this complete description gives us the multicast protocol. And we call this multicast because the C0 is somewhat trying to copy the qubit that V0 sent to the switch. If the switch sees a 0, the state is 0. If the switch sees a 1, the state is 1. And we can use this multicast protocol to estimate the bit flip probabilities. The observations are that obtained by V1 and V2 are essentially one bit of each, right? Because V1 and V2 both performed a Z basis measurement on the qubit. And then the probability that V1 will measure 1 is theta 0 times 1 minus theta j, meaning a probability of no flip occurring in the first channel and a flip occurring in the second, plus the inverse of this, that is a flip occurring in the first and a flip not occurring in the second channel. Then this is true also for V2. And when we ask ourselves what is the probability that both V1 and V2 will measure a 1 after performing a Z basis measurement, we obtain this equation here that has the same rationale as the preceding equation. Both of them will measure a 1 if no flip occurs in the first and a flip occurs on the channel E1 and channel E2, or the opposite of this, that is a flip occurs here and no flip occurs in these two channels. Then we can perform some algebraic manipulations on these probabilities of measuring 1 in individual measurements and in the joint measurement. And we can obtain a set of equations that of this form here, where theta j, which is the probability of not flipping a bit of a channel, to be equal to the probability that we're going to measure 1 in an n node minus theta naught, which is the probability related to this first link here, divided by 1 minus 2 times theta naught. And another equation that only depends on theta naught, and that is a degree 2 polynomial. And what the degree 2 polynomial here that only depends on the probability of flipping a bit on the first link, it yields us two possible solutions for the vector theta 0, theta 1, and theta 2. And the answer for this is very simple. It's just because this is a degree 2 polynomial, which has two solutions, two roots. And it's very simple to check that if you have a value theta star that is like for which this equation holds, the value 1 minus theta star will also hold for this same equation. There's a symmetry here in this case. And this means that if we run this multicast protocol and we will attempt to obtain estimators for each one of the probabilities of flipping bits in each one of these links, we'll have two different sets of solutions, two different solution vectors that are equally explained by our observations. And before we go to the poll question, this just means that we don't have identifiability right away in this case, in the way that I told you about, because we do have two solutions, not a single one to each one of the parameters characterizing the links. So let's go to our poll question. That is, how many estimates theta hat we have for the parameter vector theta when we have a star network with 3 n nodes, and then we are using the multicast protocol. A, 1 solution. B, 2 solutions. 3, no solution. And then D, 3 solutions. Okay, so I think we see mixed answers in this. We see some answers on 2 and some answers on 3. And the actual answer is 2 solutions. We are really trying to estimate 3 parameters for each one of the channels, but we have 2 solutions because we see 2 vectors, theta 0, theta 1, theta 2, following these observations. So the answer is really 2 solutions. We have 3 parameters, but we see in total, let's say, 6 possible 6 numbers, 2 vectors of numbers that are equally explained by the observations from measurements. All right, so then I think this leads to a very fundamental question following this multicast idea, that is, how can we achieve identifiability in the sense of how can we actually find a single solution, a single parameter, a single vector of parameters that will tell us the state of the network, meaning the bit probabilities for our links. And the potential ways to do this are, we can use an additional assumption. Let's say we can say that the probability of flipping on the first link is high, meaning that probability of not flipping, which is theta 0, is smaller than 0.5. And with this assumption, we can decide which of the 2 vectors we have. We could attempt to distribute different states, meaning change the distribution protocol that we use, the multicast protocol, to a different protocol, and see if this protocol gives us identifiability out of the blocks, or we can, let's say, combine observations from different states that are distributed to be able to find a single solution for the vector parameters. And what I'm going to tell you here is the independent encoding distribution circuit that uses the second idea here. It really distributes a different state among the n nodes to be able to identify with flip probabilities. So the circuit looks somewhat like the multicast circuit, but instead of just sending a qubit right away, the root will prepare a Bell state. It will keep one of the qubits stored and send the other qubit to the switch. Then the switch will perform an operation that qubit. Then from this point onward, it is the same as the multicast protocol. And once this is done, the n nodes and the root will perform a measurement. And in this case, a very special type of measurement that requires entanglement share between these 3 n nodes, and which is this thing that we call a GHZ measurement, is a measurement on a GHZ basis. And with this protocol, which is very similar to the multicast circuit, we are actually able to identify a bit flip probability for each one of the links. And it turns out that the encoding we have by using this particular circuit, it's a very nice encoding where the probability of seeing a 1 in each one of these n nodes is the probability of flipping the bit in the channels. So whenever we see this bit here to be 1, this classical bit, this means that flip occurred in channel A0. When you see a 1 here, a flip occurred in this channel, and when you see a 1 here, a flip occurred in this channel. There's a slightly a typo here. Really, this should be the probability of seeing 0 is theta I, because we're defining theta sub I to be the probability of not flipping when the qubit traverses channel I. Okay, so let's look at how this protocol, the independent encoding protocol works if we're simulated. So what do we have here? This plot show us the estimator value, meaning the values of theta that we obtained based on the number of samples that we used to estimate theta. And what is nice about this is that we see that with somewhat couple hundreds of samples, our estimators already approach the benefit probabilities that we have for each of the channels, which in this case are here 0.8 for channel 0, 0.3 for channel 1, and 0.2 for channel 2. And 0.4. And what is nice about this protocol is that the number of samples that we must use in order to estimate all the benefit probabilities in a star grows linearly with the number of nodes that we have in the star, and is in fact an efficient procedure to estimate the benefit probabilities, since it gives us a polynomial complexity to estimate probabilities as the number of channels grows. We did use entanglement to perform the spatial measurement that I told you about, meaning in order to fully execute this route-independent circuit, we need the end nodes to have pre-shared entanglement distributed between them so that it can implement that spatial measurement. This can be waived by with the cost of doubling the sample complexity that we have to obtain the same efficiency. Meaning, if we could use 500 samples to obtain this efficiency here with entanglement, we can use 1,000 samples and perform measurements that can be done independently by the nodes and still obtain identifiability with the efficiency that we had for 500 samples when we use entanglement. And what is nice about this, again, is that this method will generalize to stars of an arbitrary size of end nodes. And if you want more information, you can read this paper here that discusses exactly how we can generalize stars with bit flips with any number of end nodes, and that even addresses different ways to obtain identifiability in addition to just using different states. Okay, so now let's go over a quick poll question. That is, what are the consequences for estimation when pre-shared entanglement is not available and the independent encoding distribution protocol is used? So we have here this possible answers. The parameters are not identifiable. Our complexity increases quadratically with the number of n nodes. Our complexity is the same as when we were using multicast, but now, is the same as when we were doing measurements with entanglement, but we just need the double amount of samples to obtain the same efficiency. And finally, D is that the complexity will grow exponentially with the number of n nodes. Okay. So the answer is that the sample complexity is the same, but it really doubles the number of samples you need to obtain the same efficiency when you're not using entanglement. Parameters are still identifiable because, as I said, we can still find the same a single solution vector following observations. The complexity will need particularly nor exponentially with n nodes. We really just need to double the amount of samples we have to obtain the same efficiency as we would obtain if we use entanglement for measurements. Okay, and how can we actually now use this idea that we defined for a star to characterize more complex networks? Well, recall that stars are a particular type of trees, and the state preparation can be generalized to rooted trees of the network graph. We can characterize links in this tree using end-to-end measurements. Then, if we perform a graph tree covering of the network, meaning covering the graphs with different trees, let's say, for instance, selecting this tree depicted here by these red arrows and this tree here depicted by the blue arrows, we can characterize the links in this network based on end-to-end measurements following the protocols for the individual trees. And once more, this also works for two-way quantum network architectures, even though I really described the protocols for one-way architectures. And what is nice about tomography is that's really an active area of research, and there are many problems to be investigated when generalizing the methods that we just discussed for stars for just arbitrary networks. So there are fundamental challenges in open in the field now. For instance, it's very important to search for optimal estimation strategies, even for stars. I just showed you two ways that you can actually characterize parameters, bit-foot parameters in stars, but we don't know which of these or which is the actual optimal distribution protocol to estimate bit flips, even in a simple star network. It is nice to find also optimal ways that we can generalize for arbitrary trees. There is a very nice problem on how we should partition a network into trees so that we can perform estimation in all of the links of a network. Maybe if we decide to partition the network in a particular way, our estimators might have a better performance. They may converge quicker to the values we're trying to estimate than if we, let's say, choose a different partition. Another interesting thing here is how can we actually compare a bipartite distribution scheme, even though I really did not talk about a bipartite way to quantum network tomography. There is one way that we can generalize or apply this distribution strategy for bipartite states, distributing bipartite states. And it would be very nice to have a in-depth comparison on the efficiency of these two methods. Another very fundamental question that would be nice to know more about is to determine what are the conditions where entanglement provides advantage. What we saw here is that when you're using the independent encoding, entanglement does provide us some advantage. It reduces by half the amount of samples that would be required to obtain a particular efficiency. But having a more precise description of really what are the conditions where entanglement will provide an advantage would be very interesting for the field. Another interesting point here is describing the conditions under which complex trees are identifiable. We just saw really one way that we can make a tomography in a star to the parameters of a star to be identifiable, and and being able to generalize this to arbitrary trees will be also fundamental in performing tomography in generic trees. Okay. Another very interesting topic of research is how to estimate this very efficient estimator for bit flips to the more generic case of Pauli channels, really where we don't have a single probability to explaining each one of the links, but now 3 probabilities explaining each one of the links. Okay, and with this, we'll end our discussion on quantum network tomography, and I will pass the floor to Don.
Okay, thank you. So the last sort of technical part is I'd like to talk a little bit about capacity, performance, and resource allocation in quantum networks. And I'm going to talk about what network capacity means and some results that are known about it, how to do resource allocation that achieves capacity, Then we've talked quite a bit about noise, and I'd like to talk about how you might do scheduling to mitigate against memory noise. And then at the end, I'm just going to touch a little bit on the problem that arises when you have flows and you need to schedule the swaps so that you generate an end-to-end entanglement. And also related to that, how you might want to or need to schedule distillation so that you can increase fidelity. So let me start off by looking at a quantum switch. It's here we have a picture. It's basically, in this case, the center node of a star-shaped network. You saw it in the tomography section as well. And what we have are a bunch of end users. Let me get my laser pointer. And they're connected to a switch through quantum channels. And the question that we want to ask is, how do we achieve the best entanglement rates if we have multiple user pairs that are using the switch? And how do we go about quantifying performance? And so the way that we're going to sort of answer these questions is we're going to make the assumption that we have, let's say, user pairs interested in entanglement. They generate requests for entanglement randomly. And these requests are sent to the switch, which then has to decide what to do. And let's say between user pair 1 and 2, the request rate might be lambda 1, 2, lambda 1, 3 between 1 and 3, lambda 2, 3 between 2 and 3. And we're going to be interested in a concept of stability. Okay, that what we want is that the switch be able to serve these requests such that the delays in servicing the requests are finite. Okay, and we'll say the quantum switch is stable if, let's say, all of the requests can be served in sort of finite amount of time, that you don't have like buildup of backlogs of requests waiting to be served. And associated with this is a notion of a capacity region. And you can think of it, it's the set of request rate vectors consisting of these request rates such that the switch can be stabilized. And here I have this sort of three-dimensional idealized plot where we have three pairs of nodes that are requesting entanglement. And if their rates lie within this sort of pyramid, then the switch can be stabilized and the requests can be served in finite amount of time. And if it's outside, then one or more of the user pairs are going to see increasing delays. So there are two sides of the story here. It's unstable outside of the region, and there is no scheduling algorithm that can be devised that will stabilize the system and will allow all of the requests to get finite delays. And then the second is for those rate vectors that are within the capacity region, we would like to design a scheduling algorithm that stabilizes the switch. And that's not a trivial problem. And what do I mean by a scheduling algorithm? It's really an algorithm that decides when we have a bunch of requests demanding attention, who do we swap? So the system model is going to be a discrete time system. Time is divided up into slots, as I've shown here. And during each slot, the following takes place. The links generate entanglement, let's say between the switch label 0 and node K, and it succeeds with a probability piece of K. And then once all the links have generated entanglement, the switch then creates the entanglement between two users, let's say I and J, by consuming a link entanglement between itself and user I and itself and user J, and that succeeds with a probability Q. Okay, and if you remember earlier when I was talking about quantum network, I was saying something about deterministic swaps. Well, here is a system where not all swaps succeed. And as I said, there are a number of quantum technologies that are being explored for the purpose of building these switches where swaps are probabilistic. We'll assume entanglement requests are described by sequences of random variables where a sub I j of t is the number of requests that arrive randomly at the switch at time t. And as I showed in the slide before, they arrive at a rate lambda ij. Okay, so that's the model. We'll assume all the memories are perfect. The gates that are used for swaps are perfect, and that all of the nodes have an infinite amount of memory. So it's sort of an idealized model, and I'll say a little bit shortly about what happens when these assumptions are violated. Okay, so here's the kind of result that one can show for a system like this. The capacity region is the set of all vectors, the lambda ij's, that satisfy this very simple inequality. The inequality holds for every link j, and it basically says that the probability that the link can generate an entanglement in a slot, P sub j, is larger than essentially the demand for it. And so let me just walk you through what the demand is. The expected number of swap attempts that you're going to get per successful swap is 1 over Q. Think of it that you attempt to generate a swap, you fail with probability Q, and so if you go back to a sort of simple probability, the number of attempts required is a geometrically distributed random variable, and the mean is 1 over Q. So that's the average number that you have to generate. Okay, if we look over a long period of time t, then roughly we will require lambda ij times t, that would be the average number of requests that arrive at time t, divided by q, so that the total is now the average number of swap operations that required. And for each of those, we consume a link level entanglement of, let's say, on link I and on link J. Okay, and so if we now sum over all of the links I, we get this sum right here, which has to be less than or equal to the number of pairs that we generate of that bell pair for that link J, and so that gives you this expression. Okay, so that's the capacity region. Now the question is there a resource allocation policy that we can use that could stabilize the switch for any rate vector there? And I'm going to present what is referred to as a stationary resource allocation policy. And what we're going to do is every time a link level bell pair is generated over link I, we're going to label it as belonging to user pair ij with a probability Fij that's proportional to the arrival rate of requests for user pair ij. And it's normalized by the sum of all the arrival rates for all links j. Okay, and because these lambda ij's are less than 1, the sum is less than 1, it turns out that this Fij, this probability Fij, is going to be larger than or equal to the probability, the rate for user pair ij. Okay, and let me just point out that I've done it, let's say, looking at ij, but it's exactly the same as if I were looking at the user pair as ji. And now what we do is anytime we generate these link level bell pairs and we've labeled them as ij, we swap them. Okay, and that will generate an end-to-end bell pair for user pair ij. Okay, so why does this work? Well, after a long period of time t, roughly speaking, p sub I times t bell pairs on link I will be generated. Okay, and we're going to assign a fraction of those Fij to ij, and the average number of attempts that's required is 1 over p sub I. Okay, and so this is going to be larger than lambda ij over t. The p sub i's cancel out, and we're just left with essentially the way how we had defined this labeling probability of Fij. And likewise, the same thing holds for link j, that we essentially label a similar number of the bell pairs on link j as ij. And so when we swap, that yields that the fraction that succeed is over the interval of time t is larger than the average number of requests that we got over time t. Okay, and I'm not going to go through the proof of this, that the algorithm actually does stabilize the system. It relies on something that's referred to as Lyapunov stability theory, and you can find details on it in this publication right here. Okay, so just some remarks about this. Suppose that these lambda ij's are strictly in the capacity region. Okay, they're not lying on the boundary. Okay, then we're going to label over a long period of time t, we're going to label t times Fij as belonging to user pair Ij, and that's larger than the average number of requests, or the number of requests that we expect to get over that interval of time t. Okay, and so when we do the swaps, we're actually going to be swapping at a higher rate than user pair I and J will need bell pairs. And so since the end nodes have an infinite amount of memory, they can store these excess bell pairs and allow them to accumulate. And in doing so, then what we find is that we can actually provide zero latency service, let's say, using this particular resource allocation strategy. There was a question about providing some capacity resource allocation references in a quantum network. And what I would suggest is to go to this paper here as a start. And that will also contain some references to other papers that are concerned about capacity. Okay, so that brings us to the following poll question. If a scheduling policy stabilizes a quantum switch, option A is it provides the largest possible fidelity to end users. B, it maximizes entanglement rates between users. C, it guarantees that user requests for entanglement are served in a finite amount of time. Or D, it provides sort of a fair share, equal entanglement rates to all users. Or E, it's you're not sure what's going on. Okay, so we've gotten a bunch of answers, and I would say that most people understand what stability means in this case, namely that when the policy stabilizes the quantum switch, it's able to guarantee that user requests, let's say, fall within the capacity, are served in a finite amount of time, or namely answer C. So let's look at some extensions to this work. We looked at sort of like an idealized setting where lots of memory, everything worked nicely. And so another extreme would be that, let's say, a qubit decoheres after just one slot. In other words, if you generate a bell pair, you have to use it that slot or you lose it. And I'll just say that that's a model that has also been examined, and the capacity region for this has been characterized. I'll just say that it turns out to be much more complicated than for a switch where you have an infinite amount of memory. And here on the right, I've sort of put a two-dimensional plot. It's just sort of idealized, where, let's say, we're plotting the rate of one user pair and with the rate of a second user pair, and we have two capacity regions, one delineated in blue, the other in red. Think of it, the blue one might correspond to the case where you have an infinite amount of memory per link, and the red one where you just have one memory per link. And what this result coupled with the other result does is it essentially gives us these two capacity regions. And so any system that has, let's say, better quality memories or more than one memory, the capacity region is going to fall someplace in between. I should mention in this case, the policy that stabilizes the switch is what's referred to as a max weight policy. And basically, it corresponds to that you have a matching pi that maximizes this sum right here, where Q sub ij you can think of as the number of requests for ij entanglement. Okay, and so think of it as the following: pi ij is equal to 1 if you decide to swap I and j. Of course, Q is the probability that it succeeds. And you can think of Qij as sort of a weight that's associated to user pair ij. And so what we're doing then is we're finding the matching pi ij that maximizes this. And that determines what swaps take place. Another direction that has been pursued is accounting for noise. And here, it's also possible to characterize the capacity region, let's say, where you have two policies. One that does end-to-end distillation. In other words, you create link level bell pairs, you swap them, and then the user pairs do distillation, excuse me, across their what they own to increase the quality. And the second one, policy B, is where distillation is done at a link level, and then you sort of generate these higher quality bell pairs at the link level that you then distill. And what I'm showing in this plot here is the capacity region. In red, it's in the case where you have no noise and you don't have to worry about the fidelity of the bell pairs that you're generating. And then in green and blue are the capacity regions that you get with these two policies. And it's interesting to see that there's, of course, a huge hit in capacity once you have to worry about noise in the bell pairs. And it turns out that max weight policies achieve the capacity region in the case where you have noise as well. In future directions for this is the kind of noise that was dealt with in this work was really gate noise, but not memory decoherence. And another direction is that almost all the work on capacity has focused on just the capacity of a single switch and not on the capacity of a network. So the challenges here are really to extend to the network setting. I'll say that in the case where the paths are given to you, its the characterization of the capacity region is not too hard, but the development of efficient scheduling algorithms is very challenging. Solving that max weight optimization problem is computationally intensive. we've really looked at the case where the user pairs are homogeneous in terms of what their requirements are, but you could have applications with very diverse requirements, let's say in terms of fidelity, in terms of latency. And so that remains to be looked at. Okay, what I'd like to do now is to look at the effect of memory noise. And I'm going to do it in the context of sort of a teleportation case study. So let's go back to teleportation. And what we want to do is we have Alice and Bob. Alice is going to be generating, let's say, qubits that she would like to teleport to Bob. And the data qubits that she wants to teleport are going to be placed in a memory. We know from with teleportation that we need to generate bell pairs between Alice and Bob as the resource that's used for doing the teleportation. So those bell pairs have to also be placed into memory. And these the generation of these data qubits or the bell pair qubits are not going to be synchronized. They're going to be random. And so you will do the teleportation when you can pair them up. So as an example, Alice might generate a data qubit. It goes into the data memory. Maybe Alice generates another one that that comes in, gets placed. I've allowed the first one to fade. That sort of corresponds to like its fidelity is degrading. Finally, Bob and Alice generate a bell pair, goes into the entanglement memory, and now we can essentially pair it up with one of the data qubits, and it gets teleported to Bob. And it ends up losing some fidelity. It's started off dark red, but it's has faded by the time it gets to Bob. And so the question that we're interested in is how should we schedule these bell pairs and the data qubits so that we get good fidelity in the teleported qubit. And two options are to either, let's say, schedule the oldest qubit first or the youngest qubit first. And so we're going to look at that. And then the other thing is that these memories are finite. And so it's possible that they might fill up. And then the question is, how do we manage them? Should we discard, let's say, an arriving qubit and just keep whatever is already there? Or should we throw out, let's say, the oldest entry, the oldest qubit? That would correspond to what's often referred to as a push-out policy. So those are the questions we are going to answer. But first, I want to talk about modeling decoherence in the memories. We talked earlier about how fidelity is a widely used measure of degradation due to noise. And it turns out that it's relatively easy to compute for many memory noise models. Okay. And so suppose that T is the time that, let's say, a qubit spends in a memory, or either a single qubit or a bell pair. And T2 is the memory decoherence time. Then it turns out that the fidelity of a qubit that has spent time T in memory is given by this expression here, a constant plus a term that has is exponentially decaying in the time that the qubit has spent in memory. And the rate at which it's decaying is the inverse of this memory decoherence time. Okay, and these constants A, B, and T2 depend on the noise model that you use, the qubit or the quantum state that you're storing in memory, and it also depends on the kind of technology that you use to implement the qubit. Here, A plus B is equal to 1. And what that corresponds to is if T is equal to 0, then the fidelity is equal to 1. So the assumption is that when we place the qubit into memory, it's perfect, but its fidelity degrades over time. Okay, so let T, uppercase T, be the time the qubit spends in memory. And suppose it's a random variable that has a probability density function f of t. Okay, well, associated with a probability density function is what's referred to as a Laplace transform. And the Laplace transform for this random variable t is just given by this expectation here. It's the expectation of e to the minus st for s greater than or equal to 0. It turns out that Laplace transforms are very, very useful in probability because they can be used to efficiently compute moments like the average and the variance and higher level moments. In many cases, it can be used to compute the probability density function, if you know what the Laplace transform is. And moreover, it provides you sort of like a nice way of composing sums of random variables as products of these transforms. That's not why I've introduced it here, but it's why it's sort of like very widely used. Okay, so let f be the fidelity, and f is a random variable because the fidelity of the qubit depends on how long the qubit spends in memory. It turns out the average fidelity is going to be given by this expression here, where I'm just averaging over this term using the probability density function for the memory time. But if I look at this, this is just a Laplace transform. And so it turns out the average fidelity is a very simple linear function of the Laplace transform for the memory qubit lifetime distribution in memory. So what that leaves us with is just the task of figuring out how long either theta qubits or the Bell pair qubits spend in memory before they're used for teleportation. Okay, and so we're going to assume a very simple model that teleportation requests arrive according to a Poisson process with a parameter lambda. And they're placed in a memory that's of size b sub r. Bell pairs are generated according to a Poisson process with a rate mu, and they're placed in a memory of size b sub e. By the way, this assumption of Poisson process is really, for Bell pairs, is consistent with the fact that Bell pair are generated probabilistically with, let's say, what we saw across a link with some probability P. And if P is small, the probability you successfully generate a bell pair over a link is small, then the time between generating bell pairs is sort of approximated by an exponential random variable, and that gives you a Poisson process. For those of you who are familiar with Markov processes, you can now model this behavior, this system, as a birth-death Markov process. And think of it that the state of the system is you keep track of the number of data qubits that you want to teleport, and that ranges from 0 to the maximum that can fit in the memory. That the rate at which you add a new data qubit is just this parameter rate lambda. And the rate at which you sort of teleport is the corresponds to mu, the rate at which bell pairs are being generated. Now, this right-hand side corresponds to the case where data qubits are being stored in memory. You can have a situation where there are no data qubits and bell pairs are now being sort of like stored into memory. And that corresponds to this left-hand side right here. And so think of it that, let's say, if we have state is -2, it means that 2 bell pairs are in memory waiting for a data qubit to come in ready to be teleported. Okay, so it turns out that these kinds of probabilistic models are very easy to solve, and you can use it to generate distribution for the number of occupied memories, whether they are teleportation requests or they're bell pairs. You can use them to very easily generate the distribution and Laplace transform for the times that qubits reside in memory prior to teleportation. Okay. And then you can just use the result that I had here to generate what the average fidelity is of the final teleported qubit. And so here's just to give you a flavor of kind of results. So, okay, we have the data qubits are being generated at rate lambda. Bell pairs are being generated at rate mu. I'm going to use lambda over mu to correspond to the load on this system. We'll assume that initial entanglement fidelity is 0.9, that data qubits to be teleported have perfect fidelity. The fidelity decays exponentially in time according to the expression that I gave before. And let's say we can store 10 qubits. And we're going to look at 2 policies, youngest qubit first and oldest qubit first with push out. And in this top graph, I'm showing what the average fidelity is after teleportation as a function of load. If the load is less than 1, then we're generating bell pairs at a higher rate than the data qubits that need to be teleported. And if it's greater than 1, it's just the opposite. We're generating data qubits at a higher rate. And this red curve corresponds to the average fidelity that you get by using oldest qubit first. The blue, using youngest qubit first. And I'd like to point out that the youngest qubit first always outperforms oldest qubit first. And we have sort of interesting behavior like, if we look at the youngest qubit first, the fidelity is high when the load is low or very heavy. And the reason is that in the case where the load is very low, we always are generating bell pairs very quickly. And so when a data qubit comes in to be teleported, there's always a very young bell pair that can be used. When the load is very high, it's just the opposite. We're generating data qubits very quickly. And so when a bell pair gets generated, there's always a very young data qubit to be teleported. And in between, it turns out that they're a bit older, and so the fidelity is not so good. This bottom graph really corresponds to just what the teleportation rate is for different buffer sizes as a function of the request rate. And let me just say, you can show that the sorry, that shouldn't be oldest qubit first. That should be youngest qubit first, with push out is provably optimal. So I have it right on this slide. The youngest qubit first with push out maximizes the entanglement rate and average fidelity. And the intuition is just that with push out, you're forcing out the oldest qubit that has the lowest fidelity. And with youngest qubit first, you're always selecting the qubit with the highest fidelity to either teleport or to use as a bell pair resource. Okay, and so here we have a polling question. Why is youngest qubit first preferable in a quantum network? Is it because it reduces the time to serve a request? Maximizes average fidelity? It's the only scheduling policy that's supported by current qubit technology, or because it doesn't require any classical communications. Okay, I'm going to end the poll. And the answer is that it maximizes average fidelity. Okay, let's go on. Some challenges that arise here is, so youngest qubit first is optimal in this very important teleportation scenario. And so it's an open question as to like how universal this result is. And we talked about how you could use these sort of very simple Markov models to analyze teleportation. And so there's an interesting question of like, you know, can you use these same techniques to look at sort of more complicated network scenarios? And can the models account for a bell pair generation, let's say, over a network, and account for like the classical communications that's incurred in teleportation? Okay, one last thing that I want to talk about, it has to do with swap and distillation scheduling. And this is going to be sort of high level, really to sort of raise consciousness about what is sort of an important and perplexing sort of problem that is going to face us in designing quantum networks. I'm going to look at 3 swap scheduling policies. One that's referred to as swap as soon as possible, or ASAP, and I'll show you what I mean in the next few slides. Another is sometimes referred to as cascaded swapping or sequential swapping, and then something that's called nested swapping. And let me start with ASAP. And here we have a linear repeater chain with between two users. Think of these diamonds as repeaters between user pair, the red and blue. And the link resources are being given just to a single flow. And what ASAP, the way it behaves is the link level bell pairs are generated in parallel, but it's probabilistic. Okay, so we might have a bell pair that's generated for this link here. Notice that time is running up. Next one is generated for this bell pair. And, excuse me, for this link here, and also for this link. And what ASAP means is that as soon as this bell pair is generated, these two are swapped. And so we end up generating this segment right here. Okay, at the next time instant, this link level bell pair is generated. And so a swap takes place and we end up generating this. And then finally, this link generates a bell pair. And so we swap and we generate it end to end. Okay. It turns out that if you're going to have memory decoherence, for example, you have a qubit associated with this bell pair stored at this repeater, and it's going to decohere until we finally do the swap at time 4. And so one can show that the fidelity decays exponentially with the number of repeaters. On the other hand, it requires the least amount of time. It requires because everything's being done in parallel, it requires the least amount of time as any swap scheduling policy to generate the end-to-end entanglement. One other thing that I want to point out is there are only 2 places that you can do distillation if you want. You could distill at the link level before you finally swap, or you can generate at end-to-end once the end-to-end bell pairs have been generated. Here's a sort of a slide showing the operation of cascaded swaps. And here, we're going to assume that bell state measurement success probability is less than 1. Okay. And with this scheduling policy, swaps are executed sequentially. Okay. I should have shown we generate a bell pair from 0 to 1. Then from 1 to 2, we swap and we get the bell pair between 0 and 2. Generates a bell pair between 2 and 3, swap, and extend from 0 to 3, and then likewise do the same thing until we have it end to end. And notice the probabilities of these succeeding are proportional to the rate, the rate at which this succeeds is proportional to the bell pair generation rate for a link, but times the probability of a successful swap to a power that's given by the number of swaps that had to take place. And so the capacity decays exponentially in the number of repeaters if we have n repeaters. And unfortunately, the fidelity also decays exponentially in the number of repeaters. It's interesting to ask, if we want to do distillation, where can they occur? And we can always distill at the link level. And then we can always distill at each of these sort of segments that grow by one link each time. Okay, the last swap scheduling policy is nested swaps. And lambda is the rate at which we're generating link level belt pairs. And what we do is we swap link level belt pairs at 1 and at 3, but not 2. And once these succeed, then 2 swaps these sort of 2 hot belt pairs that connect to it. And so for a path of length n, it turns out that you can show that the rate that you get now is lambda, the link generation rate, times the success probability for swap. But now instead of to the power n, it's log n because of this sort of nested structure. And so that gives us sort of a polynomial scaling. And one thing it does is, because we know exactly where the swaps are going to take place, we could also distill at each of those levels if we want. And so what we have is, let's say with cascaded, we had an exponential decay, but with nested, we have a polynomial decay. And so we get a much higher capacity with the nested swap. And notice when Q is equal to 1, then you actually get sort of distance independent rates. The dependence on n disappears. And so looking at these 3 sort of swap scheduling policies, entanglement scheduling can affect performance. If we look at nested swapping for, let's say, homogeneous repeater chain, where the chain is exactly 200 kilometers long, but what I'm going to do is we're going to vary the number of repeaters on that chain. Then we have the following kind of performance. We're looking at entanglement distribution rate as a function of the number of repeaters, but again, where the total distance is 200 kilometers. If the swap scheduling success probability is high, close to 1, we see that we get almost distance independent rate. And as the swap scheduling success probability decreases, then we start to get a decay, but it's a polynomial decay rather than an exponential decay. Okay, so to sort of recap this, with ASAP, it turns out you get the lowest latencies, it takes the least amount of time to generate an end-to-end entanglement. Turns out that it's very difficult to analyze, especially for probabilistic swaps. And so I'm not quite sure that it's really known exactly what the capacity is as a function of path length. And I think a downside of it is that you can only do link level or end-to-end distillation with this. Now, one reason I sort of presented this is that this is a very popular swap scheduling policy because it seems very natural because of the parallelism. But as I said, I'm not sure it's really clearly understand. With sequential, you get the highest fidelity. Unfortunately, the capacity decreases exponentially fast in N, but it's the most easily integrated with routing. And because you can think of it as if you're routing, let's say, an entanglement generation request hop by hop. And what's happening is every time you go one more hop, you're extending the bell pair from the end node to that node. And so I think that it may be possible to borrow results from classical networking to apply to a network that supports sequential swapping. And this permits, it's more flexible in terms of distillation. You can do it at the link level, or you can do it at each of these segments, or you can do it end to end. Nested swapping gives the lowest fidelity, but the capacity decreases polynomially in N, and it presents the greatest flexibility for distillation. Okay, and so I'm going to stop here. Just want to. So the challenges are, how do you extend this to multiple users? I really sort of presented it in the context of like a single user pair, and to networks where you integrate with routing. How do you handle noise? One of the interesting things is that you might want to maximize the entanglement rate subject to, let's say, a minimum fidelity constraint. And then how to sort of introduce distillation as part of the optimization. And how to really account for memory constraints in the network and the multiple user setting. And I'm going to stop here and hand it over to Matheus to sort of very quickly present the summary.
Thank you, Don. So let me just share the screen. Okay, yeah. So now let's go quickly over the summary of everything we discussed and recap some of the open challenges that Don and I mentioned throughout the presentation. Well, so let's start with what quantum really brings to the table when we're talking about networks. The first thing that we saw is that the rates that we can distribute entanglement really decay exponentially with fiber if you're just trying to send quantum information directly. We saw that we cannot use classical ideas for overcoming this strong attenuation because of the non-cloning theorem, since it prevents us from copying information and just trying to beat the exponential decay by simply sending the same a copy of the message multiple times through the channel. It's also important to note that quantum information is extremely fragile. This really brings to the table the notion of quantum error correction and distillation, which are fundamental for any sort of quantum network that we might come up with. So we really need to have a way to beat the depleting effects of errors and noise from the memories that we have, from the noise introduced by the channels, the decoherence in the memory, so on and so forth. And again, we are in the Niski era, so quantum hardware is noisy, and we will need to deal with this noise whenever we want to perform meaningful quantum communication. What we saw from classical networks, we started discussing packet and circuit switching, and we saw that circuit switching deals with a way to allocate channel for users that requires an initial setup of connection, and it was really used for telephone networks, while packet switching takes into a different approach, and it tries to provide with the channel bandwidth. You really think about communication performed in packets, and these packets use entire bandwidth as they are transmitted across a channel, and this really enables networks to serve many more users in a more efficient way than circuit switching does. We saw that classical networks are analyzed through in a layer design, where layers perform specific services, and there are different protocols that operate in each one of these layers, and we call this a protocol stack. And when we put this stack of protocols together, we are actually able to perform end-to-end communication in a classical network. We saw the application layer that has some particular protocols such as HTTP, which is used for us to access web pages in a browser. We saw the transport layer that uses protocols to do the transport of bits from one end node to another one. The network layer that is the network responsible for routing information across the network. The link layer, that is responsible to transmit information between two endpoints, and the physical layer, which is essentially the actual electric signals being propagated in a link within a network. We also saw that a fundamental idea used in classical networking is store and forward, which is really what it's brought by when you look at packet switching. In a store and forward network, the switches will receive a packet, will store this packet in memory, look at a routing table and see where this packet must go, and then transmit this packet to its according port. We also saw that there are plenty of routing problems and resource allocation in classical networks. For instance, shortest path routing is one way that we can do routing. The IP protocol, for instance, that is performed by the network layer. We also saw something very interesting, that the internet is formed by a connection of multiple networks, and those networks have different scales and different they provide different services after all. So we saw that we have tier 1 ISPs that are provide the backbone for the network. We saw tier 2 SPs that communicate with tier 1 ISPs in a service-based approach, meaning they really pay for service for tier 1 ISPs. And then we saw that as we approach the users of the network, we have smaller networks that are usually local, and that when we put all of this together into perspective, we see that communication between end nodes, really a single packet crosses multiple different networks when it's sent from one end node to another one. Now, for quantum networks, we really saw two different ways of performing information transfer. A one-way approach where the state of a qubit is directly sent from a node to another one. And we saw the two-way approach where we first distribute a veil pair and perform teleportation to send quantum information. We saw that we can create a quantum network with quantum repeaters and quantum switches, and really partition the communication into two steps. One, that we generate link level entanglement between neighboring nodes, and the other step where we perform entanglement swapping, which you can imagine as a Bell state measurement performed inside a quantum switch or a quantum repeater to propagate entanglement towards the end nodes. We also saw that it's very important in a quantum network to try to mitigate noise, and that there is noise in memory and noise, for instance, decoherence in memory. Once we prepare a link level entanglement, the quality of this entanglement decays as we keep this entanglement stored in memory, and also in transmission. Let's say, for instance, when I talked about quantum network tomography, the bit flips that a channel can induce into a qubit are detrimental for quantum communication, and mitigating noise is extremely important. So we briefly discussed about how purification consumes multiple entangled states to generate one quality entangled state between two nodes. And this also works, of course, to mitigate noise from both memory and from the channel. We did not really talk about control plane, but in extreme detail. But you can imagine that scheduling swap operations is part of a control plane, and that a quantum network will need a control plane after all. So you can imagine that any routing operation that must be performed is a decision that has to be taken by some control plane algorithm, and swaps are part of this notion, right? When just selecting which a qubit is going to be swapped, which are the two inputs of a Gauss state measurement, for instance, is something that the control plane must do. And also, it is still an open question on what is the proper layer structure that we should use to talk about quantum networks. We saw one particular example of how we can divide quantum communication into layers, but again, this is not a de facto answer to the structure of how the quantum network will look like, or the quantum internet. There are plenty of open challenges in the field of quantum networks. For really, it's fundamental to try to design efficient quantum repeaters that can scale, so that you can, let's say, create a quantum network interconnecting cities or even countries. And the quantum repeater is essentially the first device that needs to be, or the fundamental device that is to be created in order for us to be able to see full-blown, large-scale quantum network working. Another very important field or set of devices that must be created for a quantum network to operate are quantum interconnects, meaning how can we actually have a repeater that maybe is using, let's say, a type of memory that is not optically active, and then we need to have a way to make that particular qubit store that memory to communicate, to emit a photon, or to interact with a photon in some sense. It's also, I would say, very important for the development of the field to really progress on the definition of our layer structure, because this can help both developers and engineers and scientists to really think about problems and really help design quantum networks that will be able to scale and will be able to provide quantum communication over large distances. Also, a very important aspect in quantum communication is the design of efficient distillation protocols and quantum error correction as well, because without a way to mitigate noise, there's no way to do meaningful quantum communication. And there's a plethora of work being currently done in order to develop protocols that can be implemented with real hardware, and that it can help us to progress towards the goal of building a quantum network. As a recap for management and tomography, we saw that quantum tomography means the estimation of link parameters in a network through end-to-end measurements. And we're looked into a way of doing tomography in stars, where the channels of these stars are represented by single qubit poly channels. And what we saw in that case was that we have improvement in efficiency of estimation if we have access to entanglement. That was the case when we used our independent encoding state distribution circuit and performed these measurements. But that entanglement is really not required for identifiability, even in this simple case. It's just that it gives you an additional improvement in efficiency. We saw also that we can extend the characterization for arbitrary networks using techniques such as tree decompositions of a graph. The challenges that some of the challenges that we highlighted was that it would be nice to have efficient protocols that were actually able to characterize arbitrary polychannels in any sort network graph that you can think of to generalize the identifiability results for general trees, since that gives us a very direct way of characterizing more complex networks. And also in this context, being able to determine how we can optimize the covering of a network with in terms of trees, meaning partition the network into trees so that we can have the most efficient characterization possible, is a very interesting open challenge in the field. Finally, understanding adding loss, which is one of the major sources of errors in quantum communications, and designing protocols, tomography protocols that take loss into account that are loss resilient is also a very interesting area or challenge to try to address. In terms of capacity and resource allocation, we saw the definition of network capacity and stability, and we saw two results. One that investigates the use of a single memory per link, and one that assumed that links have or switches have infinite memories. And as I mentioned, we saw that these two sorts of regimes, where we have infinite memory or a single memory per link, provides us really a lower bound and an upper bound for the capacity region of networks, and that the taking into account more realistic models for the number of memories we have really gives us points within this two boundaries. We also saw the results with respect to scheduling teleportation and the effects of noise in the fidelity of the teleported qubits. And what we saw was that we can use youngest qubit first with push out to maximize average fidelity in teleportation. We briefly talked about routing, which is essentially how we can actually concatenate entanglement and generate entangled states across n nodes in a network. And what we looked at the end of everything was how we can actually improve communication rate in a quantum network simply by changing how we schedule swaps, let's say, in a chain or in a path. And we saw that we can have a polynomial decrease in rate with distance for a chain topology, which is just a linear graph interconnecting two n nodes, by using the nested protocol. And that we also discussed some additional ways, the swap ASAP method and the cascaded swap, which each has its own advantages and disadvantages. For the challenges in this case, it would be very nice to have a more detailed final answer when we consider noise and distillation in the definition of the capacity region of a quantum network. We saw an example where we allowed for distillation, but just distillation link level distillation or end-to-end distillation, and really considering any sort of distillation scheduling, it would be very beneficial for the field. It would be very interesting to investigate how we can do entanglement routing efficiently when we have noisy environments, which is what we are probably going to see in the near future. So having routing algorithms that can take into account the effect of noise and still be able to generate entanglement at a meaningful rate is a very exciting challenge that we need to overcome. We also finding scheduling policies for generic topologies. We're really focused on chains of repeaters, but quantum networks will not be just a line of nodes connecting to n nodes. They are going to be very much more complex graphs, and we're going to be interested in distributing not only bipartite but multipartite states, and understanding how we can devise scheduling policies to serve all these different types of requests within a network is a very nice, a very interesting thing to do. Another important problem to address is finding an optimal purification scheduling. again, we looked at examples where we assumed we could do a link level purification or end-to-end purification. And probably the optimal way of distributing entanglement with purification is not just doing end-to-end or link level, is something in between. And having a description of this optimal way of distilling is, or purifying and distilling, here we mean both of them, we use both of them interchangeably here. It's very important. And finally, as a challenge in the allocation and capacity subfield, figuring out optimal buffer management policies for general topologies, not only for chains, is also fundamental for the development of quantum networks. In the chain case, where we have only 2 users, that's a very particular scenario that is meaningful, but still it does not address the quantum networks in its full generality. So it would be very nice if we could have demonstrate that the results that we had for a chain can be carried over into more generic and realistic scenarios. Okay, and with that, I think we reached the end of our course. And I'd like to thank you all for joining us for this short course during the CQN winter school.